Okay, so let's get going here. Welcome to our main meeting for June 17th. And before we get started, here's the disclaimer. Please note that all our meetings are recorded and made available to the public for viewing on our YouTube channel. By participating in the meeting, it is understood that you have accepted these terms. So tonight on the agenda, Charlie's going to talk about LEDs, the history, the tech, and the design behind it. And then Eric's going to talk about field day at his farm. And if you're ready to go, Charlie?
I am indeed. I'll just start sharing if I can get that going.
Okay, so are we keeping our cameras on or off?
It makes no difference. Probably best to turn your camera off if you're not speaking, but it shouldn't matter with the science experiment of this evening. So we shall see. This is all right, and over here. Can everyone see my first chart?
Yes, sir.
Yeah.
All right. Crossed fingers. Things seem to be going well so far. So I got into a little bit of a rabbit hole around LEDs a week or so ago, and I decided that I would share some of the information that I found as I went down this rabbit hole. So this is going to be a little bit basic in the beginning, just talking about a little bit of the history of it and how it works and so on, and then maybe we'll get into how to design with them and things we should be doing on our circuit boards, particularly if we're worried about running on battery power or things like that. So what's an LED? It stands for light emitting diode, if you weren't aware. What it really is a semiconductor PN junction. So transistors would be an NPN or a PNP. Diodes are P and an N. And the cool thing about light emitting diodes is that when electrons go across that gap between the p-type material and the n-type material, a bit of the energy gets released as photons. There's so if you're used to thinking about light bulbs, there's no filament here, there's no gas here, purely a solid state device, purely a diode, and part of the energy going across that junction gets converted to light. So typically it has a forward voltage in the it says 1.8, but it's usually more like 1.2 to about 3.5 volts, depending on what color it is. And you need to take that forward voltage into account when you're designing with it. A standard diode has something on the order of, we typically design with 0.7, maybe sometimes it's down as low as 0.5. But the light emitting diodes, it's a little bit higher junction voltage. Historically, I was shocked to find that the very first light emitting diode, like a semiconductor that displayed electroluminescence, was discovered back in 1907. And mostly ignored. It was just kind of, well, that's cool. It's glowing, and nobody did much with it from there. 20 years later, somebody thought it was a cool idea to try and intentionally make this happen, and so a fellow actually did manage to do that in 1927, but without writing a formal paper on it and so on. Any reports that went out about it were pretty much ignored. No one really cared. Back in 1955, infrared emissions from a gallium arsenide diode was observed, and notes were made. And but in '61, someone actually filed a patent for that infrared LED using gallium arsenide. In '62, first visible red LED was demonstrated at 660 nanometers was the frequency of the red LED, and that was again gallium arsenide with phosphorus attached to it. That coating of phosphorus dragged it from being infrared outside the visible spectrum into red, which everyone could see. And then by '68, it kind of got commercialized. Hewlett Packard actually were the first ones to commercialize that red LED, and the concept of using LEDs as indicator lamps was born. And these indicator lamps were used everywhere, whether it was, power on indicators for TVs and radios, 7-segment LED displays in early calculators and clocks and so on. In 1972, the HP35 was one of the first ones that actually were bright enough to read indoors with a 7-segment LED. It became the power indicator for test equipment like scopes and multimeters, panel indicators on machinery, replacing those incandescent lamps that were fragile and frankly burned out fairly regularly, didn't do well with vibration and so on. And the LEDs lasted significantly longer, like orders of magnitude longer than the incandescent bulbs that replaced the pilot lights. Today, LEDs are everywhere, right? Our general lighting in homes and offices and streets has effectively all been replaced 99% with LED equivalents. The LED, has replaced incandescent and compact fluorescence with incredible efficiency. I mean, we're talking with the general lighting LEDs now of 50,000 hour lifetimes, 200 plus lumens per watt. Compared to incandescent, as an example, at 15 lumens per watt. So these are far, far more efficient. No more wandering around reminding people to turn the lights out. You're wasting electricity, because there isn't all that much electricity going on. LED lighting in homes used to account for a large portion of the electricity bill. That is essentially gone away. It's a minuscule portion of folks' electricity bills these days. They got used in cars too once they got a whole lot brighter, headlights and interior lighting and so on and so forth. And of course, the old displays are still being there, but now our screens that we're looking at are possibly LED. Certainly, LCDs are backlit with LEDs, and the next generation screens are all LED. Grow lights have become an interesting use for LEDs, simply because with the ability to tailor the color, the spectrum, you can make the lighting for your indoor plant growing tailored to exactly the spectrum that plants need, so that they grow amazingly well. I saw a thing on TV a while back about some of the old subway tunnels in the UK being turned into places to farm things with LED lighting of the right colors, plants for downtown restaurants that are looking for very fresh vegetables and greenery to add to the restaurant. It only has to travel a short distance if it's being grown underground and utilizing space that was being wasted. It's the ultraviolet LEDs that are now available are also being used a lot in medicine, where disinfecting instruments, for instance, if you've been to the dentist that and had a filling, that light they stick in your mouth to cure the material that he's packed in the cavity that's been replaced, that's all cured with ultraviolet stuff. And it's also used for sensing, range sensors, proximity detectors, and so on. Its LiDAR is based primarily on an LED. So they've come a long way in the last, I guess, 50 to 60 years that they've actually been commercialized. When we start to design with LEDs, basically you've got a power supply, some current is flowing through that LED, which emits light, and there's a series resistor. Series resistor is very important. If you forget the series resistor, your LED will be gone in milliseconds. You absolutely have to have that series resistor. And you choose the value of the resistor based on the supply voltage in order to limit the current to what the LED wants to see.
Charlie,
so typical LED.
Excuse me, Charlie, is your display, are you showing slides as you're going? Because we're just looking at the first one, I think, the indicator lamps. I don't know.
Oh, really? No, we're having this problem again. Okay. I've gone through like 4 slides. So thanks for bringing that up. Let me see if I can. We had this problem last time, right? So let's go back to.
As a side note, there's been no dropouts in bandwidth until just now when you flipped off your screen.
Okay. So you can see this one. What is an LED? That was a few slides ago.
Yep.
Yep.
You see this one?
Yep.
Okay. I don't know why it didn't change through all of this. Interesting. Okay. This one was the one about indicator lamps.
Yep.
Yep.
That one.
LED usage today.
No.
Anything now?
Still on. No. Still on early use.
Okay.
There we go.
There you
Current
go.
consumption.
It's changed. Okay. All right. So this is the one I was just talking about, the current flow. And as I say, the spec sheet will tell you typically that you want 20 milliamps. Certainly for the red ones, you will. There are some other ones we'll talk about in a bit. But so how you get to the 20 milliamps, very, very simply, basic stuff everybody in this group can do for sure. If you've got a 5-volt supply and you've got a 2-volt forward volt drop on the diode, then it's 5 minus the 2 is 3 volts. Divided by the 20 milliamps gives you 150 ohms, and that's the size of the resistor that you need to use. Very simple and straightforward. But that 20 milliamp number really depends on the type of LED that you're using, and also the color of LED that you're using. So let me see over here. So got a new slide. Strategies to reduce the current consumption.
Yep.
So one of the things you can do, obviously, is to reduce the current through the LED. It'll be a little less bright, but often it's still quite adequate for indicators. You can run it at 5 to 10 milliamps. And consequently just reduce the current that's consumed. I guess it's worth mentioning at this point that with 20 milliamps doesn't sound like much, but if we're out operating in the field somewhere on battery backup, 20 milliamps can be a huge portion. I mean, the Daniels repeater receivers that I've played with in the past, the whole receiver consumes 25 milliamps. So 20 milliamps for a single LED is consuming almost as much power as the as the entire receiver does on some of these low power units. So trying to get that 20 milliamps down is an important consideration, particularly if you've got limited power, like running on battery. Constant current drivers are out there, and constant current drivers, while they regulate the current precisely, they don't necessarily reduce it. Because the efficiency is so high, at least you're not wasting energy in that resistor. You're not wasting it as heat and heating up the radio, which may be in a harsh environment and doesn't really need that extra heat to be added to the problem it's living with. You can do pulse width modulation. This is a fairly common approach, and basically what it is if you turn the LED on and off fast enough, your eye integrates it, and it looks like it's on all the time. And basically, anything over 100 hertz, your eye will never detect that it's ever been off. Down at the kind of 50 to 60 hertz range, you might start noticing that it's blinking, particularly if you look away and look back. But over 100 hertz, you'll never notice it. But you can do something like turning it on at a relatively high current, just 1% of the time. And, consequently, if you cranked it up from 20 milliamps to say 100 milliamps, 1% of the time, overall, that's the equivalent of 1 milliamp, but it looks significantly brighter. And these days, lo and behold, there are ultra high efficiency LEDs. So you can buy some modern ones that produce the same brightness of the 20 milliamp ones at somewhere in the order of 2 to 5 milliamps, particularly if you get into the surface mount devices. Multiplexing is a way of conserving power that was pretty common in the 70s and 80s and 90s. Essentially, if you've got multiple LEDs like 7-segment displays, a large collection of numbers and so on, you can blink the segments on and off in the same way as you would with pulse width modulation. And, basically, if you're scanning at 100 hertz, then each segment only gets turned on. If I've got 50 LEDs, that will get turned on one out of 50 will be turned on. So 1/50th of the time, each segment will be lit up. And then number 6 was one I thought would be fun to mention, is Charlie plexing, which has nothing to do with me, but I'm always happy to take responsibility for it, show it off whenever I can, since it's my namesake. This has to do with driving LEDs from a device like a Pi or a Pico directly, and taking advantage of the GPIO pins tri-state capability to save current savings in dense displays. So as an example, here's a quick example of Charlie plexing. If I've got 3 pins, each pin has the capability of being turned on or off or switched to being an input, which makes it a high impedance state. So for instance, if I have X1 turned on, and X1 is high, X2 is low, and X3 is high impedance state, then LED number 1 will be turned on. If I change X2 to a high impedance state, X1 stays high and X3 is low, then LED 5 will be turned on, and so on and so forth. So by using that third state capability of the GPIO pins, you can actually drive a large number of LEDs with fewer pins. Just checking, you can now see the chart with perceived brightness versus duty cycle.
Yes.
Okay. So the human eye, much like the human ear, is nonlinear. The decibel scale was invented by Alexander Graham Bell because your double the power is nowhere near twice as loud to your ear. The same is true with your eyes. Things will appear brighter at lower light levels. It's kind of I believe it's a square law. So basically, a 50% amount of brightness looks about 71% as bright. The red line here is the perceived brightness, where the actual power is the gray line. So at as I said, at about 50% of the power here, it looks 3/4 almost as bright as if it does at 100% of the power. So you can take advantage of that by reducing the power in the LEDs, and even getting down here at say 25% of the power in that LED will look half as bright. Which is probably still sufficient for an indicator bulb, so that you know that there's power on in your circuit. The flicker threshold I mentioned earlier, it's on the order of 100 hertz. So if you blink faster than 100 hertz, people won't be able to see it. And at the end of the day, we can drop power quite a bit and still have a fairly useful indicator. I mentioned colors being different earlier on. This chart is talking about the different colors and the different forward volt drops. So infrared ones and early red ones had about a 1.2 volt forward drop. Then you get into on the order of 2 volts, the 1.8 to 2 for the red. Orange bumps up a little bit more. Yellow is a little bit more again. Green and yellow tend to be about the same. When you hit blue LEDs, suddenly that volt drop across it has gone up significantly. It's in the 3 to 3.5 volt drop. So if you're trying to drive a blue LED from a 3.3 volt power supply, you're gonna have a tough time, like trying to get a resistor there, and the variances in the blue forward volt drop, depending on manufacturing, it either may not come on at all, or you're certainly going to need a different strategy for limiting the current through it than trying to use a resistor. White has that big volt drop as well, about the same. And if you are into the ultraviolet, these ones, it gets even worse. You can get even up to 4.5 volts forward drop in the UV. Blue took a long time to develop. Blue was a challenge, and blue was kind of the holy grail in colors for a very long time. The reason for that is, if you want to do a color display, for instance, for a CRT replacement, well, you need red, green, and blue. Those colors mixed together are the primary colors to get all the other colors, right? So getting to a blue was a challenge, and after that, white was the other one that was a challenge, because that's what you want for lighting in homes and so on. But it was challenging enough to get that blue going, that the fellow who managed to do it in in 1993, actually won a Nobel Prize for that accomplishment. So it was the thing that really changed the industry and changed the use of LEDs for things beyond turning on a light on the control panel to let everybody know that there's power to the circuit. I talked through this pretty much on the last chart, but this is just a different way of indicating the forward voltage by color, and worth noting that as the voltages go higher, you do waste a little less power because there's less voltage to drop across that resistor. So, there's some advantages to those forward voltages. In fact, often what you'll see for the white LEDs that are used for lighting is you'll see multiple LEDs in series in order to get that voltage even higher. So, 3 white LEDs in series, for instance, will come out around 10 volts. So if you do that, you've got 10 volts dropped across the LEDs. If you want to power that, for instance, from a 12-volt battery, fairly easy. You only have a couple of volts to drop across a resistor for that kind of stuff. The low current LEDs are a relatively recent innovation within the last 10 to 15 years, I guess. They put out the same amount of light as the old 20 milliamp ones, in fact, more light, for, probably on the order of half a milliamp to a milliamp. So the old standard LED ones, they were putting out, 1/2 to 2 lumens per watt. The newer ones are, on the order of between 100 to 200 lumens per watt, significantly more light for the same amount of power that's going into them. I had to put this chart in because I'm always harping on this, that we need to read the data sheet for the parts that we're using, and LEDs are no exception. The important things to look for on that LED data sheet, and they all come with one, is the forward voltage, the forward current that's required, and note that there's a forward current and a peak current. So the forward current basically creates heat in the LED, and you want to make sure that is properly taken care of. The peak current, this is a typical red LED for these numbers, 20 milliamps all the time. If you're pulsing it, you can pulse it up to 100 milliamps. You don't want to go over 100 milliamps because, number one, it's going to overheat, and its lifespan is going to reduce significantly, like from 50,000 hours to minutes or seconds or less. The luminous intensity is something that is well worth looking at too. No point in having an indicator lamp that you can't actually look at because it's so incredibly bright. It's rated in this particular example data sheet. It's rated in millicandela. And it is beam angle dependent. That is, if you look at it straight on, it's significantly brighter than if you get off from 15 or 20 degrees. You're looking at it from the side a little bit. It's not nearly as bright. That viewing angle is something else that's specified. There's the what's called the half intensity angle, and depending on the LED you got, that could be anywhere from 15 degrees to 120 degrees. The wavelength is usually there, which is the dominant color that you're seeing. 660 nanometers would put it in the red range. Reverse voltage is also important to note. If you have an AC circuit where you've got reverse voltage across these diodes, they tend to be not very resilient to reverse voltage. So you got a forward voltage of 2-ish volts, a reverse voltage of only 5 to 6 volts max. So putting voltage across it backwards could very easily destroy it. You'll also find the maximum operating temperature specified. All our electronic devices are things that we need to be cautious of the maximum operating temperature. Diodes are no exception. Junction temperature is what's specified. And if you're lucky and you've got a good data sheet, it will also specify the thermal resistance, which basically, if you remember, we talked about this some time ago, the thermal resistance is how much higher that junction is going to be than ambient. And that's specified in degrees C per watt that's dissipated. With LEDs, the ones that are used for indicators, they aren't very good at getting the heat out. So they'll often be on the order of 200 to 500 degrees C per watt. Whereas the LEDs that are used for lighting typically have an embedded heat sink to try and reduce that junction temperature and keep it down to something below whatever the max operating temperature is. 125 is not uncommon. I have seen numbers in power LEDs up to sort of 195. The higher you run that junction temperature, the shorter its life will be. So it's good to try and keep that temperature down if it's at all possible. Those new high efficiency LEDs are amazingly efficient, actually. For a modern 402 SMD LED, is going to give you lots of brightness at 0.5 milliamp, which is about 40 times less than we got in the 1970s and 1980s. Even the 1990s, a low current LED was introduced in the 90s that but did well at 2 milliamps as opposed to the older ones at 20 milliamps. The ultra bright ones in the 2000s, they consumed a bit more current than the ultra low current ones in the 90s at about 5 milliamps, but the amount of light they put out was an order of magnitude higher. And then the new ones are in the order of 1 milliamp or less, particularly the surface mount ones. And if we just talk about the surface mount ones a little bit here, the difference in the size of these devices and their power handling capability or their current requirement is quite surprising. The original ones, the 5 millimeter packages, they were looking at 20 milliamps. The 3 millimeter ones, which some of us have been using, they should be run in the 10 to 20 milliamp range. When the SMD ones first came out, they were 1206 size. They were 20 milliamps. Then 0805, they were like the 3 millimeter ones. They were sort of 10 to 20 milliamp range. Then when they got down to the 0603 sizes, well, now suddenly you're into the 5 to 10 milliamp range, and 0402s. They were at 1 to 5 milliamps, and now the 0201s are at half a milliamp. LED driver circuits. So in the interest of trying to get efficiency of the power that we're consuming, so we're not we can reduce the power for the same amount of light, basically, to save power. There are a number of methodologies that have been used. Just the simple resistor is the one we typically use most of the time. It's probably about 50% efficient. Whereas if you dedicated a switching converter to just driving that LED, you're up in the 92% efficiency range. But that's a lot of parts to save a bit of power for an LED. Charge pump uses less power, a little less efficiency at 88%. And then you can get driver ICs that are in the 75% range, or you can use transistor current mirror designs and get in the kind of 70% range for efficiency for the drivers. When it comes to lighting in the house, I mentioned a little bit earlier, but come back to it again. Thermal management is the key. So folks who spend their time designing LED lighting for homes and offices, they spend a lot of time trying to figure out how to keep that junction temperature down. And the thermal interface material is absolutely critical. For those types of things, you want to get that LED down on a slug or some type of package to try and get the heat out of it. As I mentioned, the lifetime at 105 degrees C can be about in the order of 10,000 hours. At 65 degrees C, you go up to about 50,000 hours. So the life is absolutely related to that junction temperature, and things will fail pretty quickly without a heat sink. The material that's used for these heat sinks, there's a lot of different materials that have been experimented with, and if you're trying to do LED lighting, you can actually get printed circuit boards that have a metal core in them to better get rid of the heat that's produced by these devices. I do know a guy who was experimenting at one point with aluminum oxide, which is a very good heat conductor, not bad as an insulator, and transparent. And I used to joke with him because he's the guy that Scotty in Star Trek would be very proud of, because he was working with transparent aluminum. The white LEDs turned out to be just the blue LED plus phosphor, and the amount of phosphor that's used tweaks the color temperature. So the ones with a thin phosphor layer, these are the cool white ones that look a bit bluish. They're around 6,500 Kelvin. The old incandescent bulbs that we had in our lamp in our bedroom were warm white at 2,700 Kelvin. And you can get pretty much anything in between, depending on the thickness of the phosphor, and sometimes they put a bit of a red tint in with it. There's the pie chart here with the split of energy for heat in the junction, visible light output, phosphor conversion loss, and then UV and IR losses. So about 45% of the energy that you put into a home lighting LED, you get out as visible light. Another spec that's fairly important for home lighting is the color rendering index. What you'll find is that some of the super cheap LEDs colors just don't look quite right with that bulb turned on in the room as the only source of light. Getting that CRI correct is one of the bigger challenges for LEDs that are used for lighting. So the CRI of 80 is the target. But if you want to do photography or studio lighting, you're looking at something 95 or better. And as I mentioned earlier, 200 to 220 lumens per watt is what we're getting these days for light out of LED lights that we purchase. The lab record so far has been 300 lumens per watt, and that's the Cree XD series. And to be honest, that target's going to fall anytime as people continue to try and refine the amount of energy we get out of these things. So coming back to our designs, the things that will impact how much current we're spending for an indicator on one of our boards really comes down to, how are we driving it, and what type and color of LED we've chosen to use, right? So, if we use some of the new ultra bright ones that are surface mount, you can get down into the 0.5 milliamp for a continuous indicator. Then there's, as I mentioned, pulse width modulator, pretty easy to do. If there's a microprocessor on the board, you can use one of the GPIO pins to do pulse width modulation. Or you can go back to using a resistor and set that resistor to 5 milliamps with a fairly bright LED, or 20 milliamps. Overall, the blue line on this for comparison is what a processor with a reasonable sleep cycle on it will burn. So, as a portion of the total power, which is the green line, it makes sense to have your processor being the vast majority of that and just a little bit for the indicator. When you get down into standard LEDs using at 20 milliamps and using a resistor, well, lo and behold, the LED is using 5 times as much energy as the processor does, and or rather 4 times as much. So it's a challenge to justify, why you have to change the battery so often because you've chosen an LED on there. It will last significantly longer if you use one of the other LED strategies. And there are a couple of other strategies that are used with processors for the the Internet of Things devices, which typically run on batteries and typically are stuck in a shed or a part of the house that you don't go to very often. You can have it have the indicator, just flash briefly for example, 10 milliseconds every 2 seconds. It just basically says I'm alive. That gets you down into a very small amount of current. The GPIO pins on the on most new microcontrollers can source 2 to 8 milliamps directly without having to use a driver IC. So you can use that GPIO pin to turn it on and off without needing a resistor or a special chip or anything. Using multicolored LEDs that are all in the single package and they have a common anode. You can, give multicolored indications using pulse width modulation again in order to reduce the overall current significantly. And again, I can't underline enough, that battery life impact is a huge improvement moving from 20 milliamps down to 0.5 milliamp. I had mentioned earlier, just touch on it again, the importance of blue for displays. If you don't have blue, you can't have the red, green, and blue that are primary colors that are required for displays, graphical displays, color graphical displays that are LED based. I don't think I'll spend too much time on this one. So, wrapping stuff up, always use a current limiting device. Doesn't matter what it is. If you try and just tap the LED across for a second to see if it's the right way around or whatever, it's gone in milliseconds. You can't tap it short enough period of time to have it survive. So something has to be there to limit the current. The forward voltage rises with the color, the photon energy, and those blue and white LEDs that look cool. They're at least 3 volts across them, as opposed to the order of 2 volts for the red ones. Low current and particularly surface mount LEDs achieve the same visibility at significantly less current, something on the order of 10 to 40 times less current. Thermal management is critical if you want to play with flashlights or lights in your room. And the amount of light we're getting from those white LEDs these days, exceeding 200 lumens per watt, whereas incandescents were on the order of 15 lumens per watt, is just a spectacular increase in the technology over the last decade. It's come into its own. Just to finish off the presentation this evening, a little bit of a twist, and the twist is that I did this presentation. It's the first time I've done a presentation using Claude. I told Claude what I wanted to talk about in just a broad outline of what I'd like the presentation to contain. I can show you what I actually asked, just a single question, and I got this presentation almost exactly as is. I went through it in a lot of detail, fact-checked it all. It's bang on. It's all correct. But I did ask one question of Claude afterwards. There were a couple of charts in here that Claude had used a sketch that I eventually replaced the sketch with an actual photograph. And why Claude did that, and instead of just surfing the net and grabbing some photographs. And the answer, of course, as I sort of expected, is around copyright. It's the folks who are writing these AIs are concerned about getting in trouble for stealing pictures and so on from the net. So Claude suggested that either I add my own in, or I could give him a collection of photographs to pick and choose from, and he could use his own, use those, or even search for pictures on the web and then replace those pictures with a URL, which I didn't think was a great way to go. So I just cut and pasted in the couple of photographs, but I made no changes into the text. I made no changes into any of the facts. Everything was correct when I looked it up in other locations. So I was pretty impressed with how Claude did on this presentation. For comparison, Let's see if I can find it over here. For comparison, I started out doing this presentation with ChatGPT, because ChatGPT in the past has been much better at presentation. Claude is much better at science and engineering and writing code. So this in red at the top is the actual original question that I posted first to ChatGPT and then to Claude. ChatGPT gave me a long-winded textual answer, including a couple of mistakes. For instance, saying red LEDs are easier to manufacture with available materials. Well, that's not really true. LEDs, red came first because it has sort of a lowest amount of energy requirement, and it's just what was found. It wasn't trying to get the other colors was a bunch of experimenting with multiple materials, multiple doping technologies in order to get the other colors. But I went through it. Most of the facts and most of the flow of information ChatGPT here did similarly to Claude. So when I read all that, I said, "Yep, that looks great. Now, let's turn this into a complete PowerPoint deck with notes and diagrams and all the good stuff." And ChatGPT said, "Yep, I can absolutely build that complete deck." Blah, 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 blah. And it went off to tell me once again in multiple pages what it was going to put in that deck, which I'd already read it once. I didn't really want to read it yet again, going through all this stuff. Just give me the darn deck and we can work on that. So in the midst of that, it mentioned, ChatGPT mentioned that it didn't have access to being able to create PowerPoint. So I basically said, well, hey, can you use LibreOffice instead of PowerPoint? Oh, sure, absolutely. That's a great thing to do, yada, 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 and on and on and on and on. And finally I said, well, okay, enough talk. Let's do it. Build that presentation, and lo and behold, I got more and more pages of stuff that would end up being in the presentation without actually getting the presentation, even a base outline. So at that point, I just said, yeah, done with you for today, ChatGPT. And so I moved on. So I guess part of my presentation is, a bunch of detailed information on LEDs, but also using AI to produce presentations seems to be a viable way to go. At the end, I put this thing together, with going over it a couple of times to make sure everything was right and so on. I would say under 2 hours, whereas normally, this would have taken me a few days of digging away at it, coming back to it, rearranging this and that. So very efficient way to do it. That's it. Questions, thoughts?
Go ahead, Pete.
Thanks for this one, Charlie. And I found some of the same things as you did with using them to help with presentations or documentation. The AI is pretty good at that. When you mentioned early on LED life, I think you made the comment, long life. I don't know. Am I the only person in the world that has household LED light bulbs that seem to burn out way earlier than they're supposed to?
Well, you'll see failures. I think I have got a number in mind, but probably 30 or 40 bulbs in my house. And I've been running LED lights now for many years, probably 10 years. And over the course of time in that, I've seen probably 2 failures. like anything else that gets manufactured, there are more components in that bulb to run off 120 volts. A 3-volt LED running it off 120 volts. Clearly, you're going to have something in there to convert the power, and you have to have something in there to provide protection and limiting and so on and so forth. So there are a handful of other components inside that bulb, and the failure may well have been one of the components and not the LEDs.
Yeah, I did take one apart to repair it, and in the end, I didn't repair it. But it was a bit of a challenge even to get it apart. I know I've been buying this stuff up at the Rollins or the Lowe's of the world, but anyway, no, I don't buy from LA Express. Whoever said that, but I might as well. It couldn't do any worse than what Rona's doing. Okay, thanks, Charlie, for that. I appreciate it.
Who's next? I think Drew was next, right?
Yeah. Hi, Charlie. That was a great presentation and something that I really appreciate because I use a lot of these LEDs and I really don't pay a lot of attention to what I'm doing. One of the things that intrigued me a while back was infrared. And I was wondering about the infrared LEDs, whether they also have a massive power consumption issue.
I guess the answer is it depends on how you want to drive it. But the IR is that the low frequency or the high frequency end? I'm just trying to think.
Low.
Yeah, so they were actually available before the red LED, and they're in the same order of magnitude in terms of power consumption. So okay. I mean, you can drive them really hard to get them to shoot further distance and so on. But
I have infrared, like night vision stuff.
Yes.
And I, at one point, I think I bought a 1 watt infrared LED, and I didn't think it really did what I expected it to do. It should have lit the place up like crazy based on the photo multiplier. But it didn't really seem to work that well.
Yeah, they're starting to add them around backup cameras and things, right?
Well, they're on everything now. Yeah.
Yeah,
they are. Anyways, that was a great presentation. I'm intrigued about your Claude success on putting together the presentation. That's good.
Yeah, I was pleased with it too.
Thanks.
Eric?
Well, I guess 2 things. One, it'd be interesting to see what Gemini would do with it as well, right? As far as when you fed that information. Have you used Gemini much?
No, not very much. I started out with chat, a year or 2 ago, because it seemed to be the only one around. And when I discovered Claude, I've never looked back. I pay for a subscription to Claude these days, and the others aren't even on my radar anymore.
Right. Okay. The other thing is, did you? I don't think you did, because I don't recall you mentioning it, but organic LEDs, where do they fit into all this? Because that seems to be something that factors a lot into the kind of things that we do these days, the little OLED displays. What I don't know much about them. It's an organic substrate, or
yeah, it's an excellent question. I didn't dig into that, so I can't answer it. But.
No, yeah, okay. I guess I'll do a presentation on that at some point.
That would be great.
There you go. Yeah. Oh no, Peter, he's dead.
Hey, do the amplifier first.
I'll have to put that aside now. Like organic LEDs. Amplifier in the fall.
Any other questions?
Thanks.
I don't think so. All right. Thanks, Ken. Back to you.
Yeah, thanks, Charlie. That was interesting. Over the years that I haven't used LEDs for a very long time, but it's just your typical red LEDs, and put a resistor in, put an LED in, and it lit.
I started building the cards that we're putting into the backplane radio, and I've got 5 or 6 different cards, and 5 or 6 different LED strategies. I don't have any that have the same colors. We've got currents anywhere from a milliamp to 20 milliamps. They're just all over the map. So and they're all fine. They're all within spec. They're all, things to do. But we never sat down and thought about a common strategy for indicators, for instance, on this. It's when you start to build a system, you need a system design really to look at this stuff overall, and we didn't do that, and it's really obvious when you put all these boards together. They're in different places. Some are in the top left corner, some are in the top right corner, and we didn't really think it through. Michael, you had a comment? You're muted.
Sure. You commented on, I had, in the audio amp board that I'm building, I used quite a low resistor value, I guess, and you commented on that. And what I got from your comment was I would have expected the LED to have burned out promptly, but they don't. They seem to work, and I just used whatever resistor I had around and seems to work. So I don't know.
Yeah, well, you're running 53 milliamps, which is a massive amount of current to be running through an LED, and it should be overheating, and I'm sure its life expectancy is going down for every hour that you have it on. I'm surprised it didn't die right away. Although they will take maybe 100 milliamp peak. But for proper thermal control and so on, max out at 20 milliamps. And
well, I guess I'll change the resistor before it dies. Then it seems to be fine so far. I was surprised to hear what you had to say, because I thought I'd figured it out to be 20 milliamps or something. I don't know, but anyway, I don't know. I have to go look. But it's okay for now.
What value resistor are you using?
I don't remember.
300 ohms with a 12 volt.
Was that what it was? I don't remember. Charlie looked at it better than I did. Don't remember, but it's working just fine. Maybe I put the wrong value in. Who knows? Could be.
Did you buy a bag of 50?
Yeah, right.
Michael, when I put your board together, I swapped it to a 1K resistor just because I had some around. So,
well, maybe Prudence says I should be doing that, because I use the resistor I use the LED to know if the board's on. So, yeah, good idea. Okay.
Yeah, I typically throw a 1K in.
Version 2, maybe.
Yeah.
Okay, thanks. Good presentation, Charlie. Very interesting. Thank you.
Thanks.
Anybody else? Okay, thanks, Charlie. That was interesting. Up next is Mr. Eric. Field Day.
Okay, yes. So sent out a invitation last week to everybody on the WhatsApp group, as well as on groups.io. So I guess it is a week from Saturday is Field Day. So it's coming fast and furious. Had a couple of people that have expressed an interest in coming, namely Ken, who I presume will be homebrew stuff, bringing antennas, stuff you want to try, but not as Ken pointed out in a reply to the invitation. This is not about making maximum points for SOAREX for field day purposes. It's a good time to make contacts with people, because there's lots of people that are looking for them out there if you want to try out your gear. But it's whatever you want to do, bring stuff to experiment with, or even if you want to put something together, or build or assemble or what have you, work on a project. Hey, maybe it's a good time to work on an amplifier circuit. Who knows? Yeah. Had to throw that in there for you. Food, again, bring what you want, fairly low key. We have lots of food here to satisfy, but if there's something in particular you want, bring it along, food and drink. Lots of room for sleeping. If anybody does change their mind and wants to stay over, we've got several guest rooms and lots of couches and lazy boys and the like, and room to sleep outside too. So whatever you like. And that's pretty much it. So Friday afternoon is generally when we start setting things up. So I'll probably be doing things all day long on Friday, getting the gear dusted off and things up and running. So that's pretty much it. Unless anybody has any questions or.
Did you get your antenna? Did you get your antenna?
Not assembled yet. No. So the countdown is on. Week and a half.
Yeah. I'll probably be there the Friday around noontime.
Well, I'm going camping with Dave for 3 nights, so maybe I should bring the antenna along and put it together at the campsite. I have a roof rack, so I can always strap it to the roof rack for the ride home. I'm sure he'd love that. You brought what?
More junk.
I think I might do it just so I can record his expression. I don't know. Well, why do you bring a box to the camp parade that says Hustler on it? Anyway,
yeah.
Gotta keep his blood pressure up.
Yeah,
Hopefully it's not magazines.
Yep.
device.
Yeah, they don't talk about the current. They don't talk about the current limiting aspects.
It
So, like a 270 ohm is traditionally what they tell you to stick on it, right?
depends on your power supply.
Well-
From 12 volts?
Yeah.
No,
No.
that's wrong. 5 volts, 270 ohm would be about right, but
Okay.
not from 12 volts. You need, double that, triple that.
Mhm.
It's always, it's a current operated device. If you don't limit the current in some fashion, it's going to burn up. So it's take your power supply, drop of the diode. If it's a 2 volt forward volt drop and you run it from 12 volts, okay, well, now you've got 10 volts to drop across that resistor, and that 10 volts at 20 milliamps is going to be what, 500 ohms?
Yeah. Oh, that was. I didn't think of it that way.
I'm gonna have to go think about what I've done in the amplifier and just see, double check. But I may
All my problems were only LEDs. Oh,
You can wind the. You can wind
Michael,
the
you're gonna sweat over an LED. Jeez.
I got bigger problems to think about.
When you finish building the super hat and the LNA and stuff, then come and talk.
You got to go find your toroid winder.
Yeah, I'm gonna try that out too. Yeah,
Was that one of those 3D printed ones, Peter?
I can show you again, except that would irritate Peter.
It kind of looked like one. Yeah. I find those difficult to operate. The slot isn't big enough for the wire. I find it really fiddly to try to get the wire through the slot.
Oh, interesting. Okay.
Yeah.
The automated ones use a hook, right? Like a sewing machine, and
Yep.
push it up and the hook on the wire and pull it down.
Yeah, I could never find a homebrew one that would wind small toroids.
Right.
No.
Yeah, that's the challenge.
What
Well,
I was
3D
thinking,
printed
I
ones
was
are-
going to get some of the magnet wire that you can melt the insulation off, because I'm too lazy to use sandpaper, and
Yes.
I was going to use the small conductor size, like 18. I think it's 18 or something. No, it's 28.
28.
Something small. So we'll see.
Most of the ones I wind are that like that, and I can never get them very tight.
Mhm.
And I honestly don't know how, if it's a little loose on occasion, whether that's really buggering things up.
I'm surprised there isn't some company in China that you can tell them number of turns you want and they'll mail it to you for a few pennies, right?
I suspect there is.
And I just haven't found. I did a bit of hunting looking for one.
Mhm.
Well, I have that bandpass filter I bought from QRP Labs for my antenna sensor, and it has enough toroids to keep me busy for the summer.
Yeah, I've been. Wayne's board has, I think, 8 of the equivalent of those on
Yep.
it. So,
And the thing is,
I keep-
I did print out one of those 3D printed little toroid winders, and I thought, well, this will be slick. You just put it on there and it'll just go right around. Yeah, no. It's actually more difficult because everything is so small. And
Peter's
unless
got
you
a
spend
few.
most of your time doing neurosurgery, stitching, it's really not easy to do.
Yeah.
I do use a needle driver to pull the wire through, though.
Ooh, what you got, Peter? You're muted.
It's a QRP antenna tuner. I think Frank would probably remember, but this I think this would have been our third ever buildathon. So I think the first one was the keyer, the second one was the transceiver, and then the third one was the antenna tuner. And I believe Frank still uses his today.
Oh yeah.
Yes, I do.
Well, that looks like that'll handle more than 5 watts.
This is where I came up with the term Peter's toroid therapy.
Yeah.
Those are a good size, though. Not like the T37s that we doing with the other stuff.
That is true. That
Have
is
you
true.
played with the Chinese antenna tuner? The $28 one or whatever.
No, I don't need to because I got the park one.
Oh boy, let me tell you. Yeah, I think it's about an inch in diameter, but the same number of contacts on like yours. Yeah, it's nuts.
Yeah.
I will never do those again.
Well, good night, everyone.
Yeah.
All right, guys.
Thanks, Dan.
Have a good
Thanks
night.
very much.
Have a good weekend.
Thank
Good
you. Bye bye.
Bye bye now.
73 to 0.
I know.